Oh yes.
I'm scared.
The number 12.
The number 12 is a number we can find in any culture.
Row.
12,
12. That was that.
wow.
9 o'clock, 10 o'clock, 11 o'clock, 12 o'clock.
If I see 12, I'm doing 12.
12 is 12.
11, 12.
It's BC section 12-5. It's your boy, Mr. Wade, and we're about to wrap up this entire curriculum with this discussion and one more lesson after this. So, what's the theme of the day? The theme is error. Talking about error. How far off from the actual answer are you? If we actually know what the sum of this series is, we can find exact error. What if we don't know what the sum of the series is? What if it's a series that hasn't been proven yet? What about before there were calculators, right? You can estimate how close you were to the actual answer. So we'll pull in some old techniques. We'll bring in a new technique today as well. Let's go back to 12-1A, the very first thing we ever did in this chapter, other than an ed talk on stage, right? A fake ed talk, was we looked at sine of x centered at x equals 0. We wrote the Taylor polynomial that approximates the sine of x, and it gave us a nice little pattern here with factorials. We stopped at the 5th degree. We called it the polynomial sub 5, all right? Now, this is approximately equal to what? The actual function sine of x. But it's only approximately equal to sine of x for values that are relatively where? Close to the center, right? Close to x equals 0, because remember, if you stray too far from the center, this chopped up version of the infinite version is not that great, right? Okay, and this one's definitely chopped off. So, all right, sine of x is exactly equal to this polynomial that's given plus a little what? A little extra. What do we call the little extra? Error, or in this chapter, remainder. Put down remainder. Back in chapter 11, we called it error. In this chapter, we often call it remainder. So, if you have a chopped off version of any Taylor polynomial, there's some extra remainder you could add onto it and then get the exact value of sine. And the remainder could be like, some sort of negative, so it could be subtract, right? Okay, so there are 3 types of errors in BC calculus. 3 things, yet again. All right. Number 1, there's the actual error, which we've done before. 12-1b, we looked at x equals 2. We wanted to find what is the error of sine of 2 compared to stuffing 2 into this very short polynomial and getting a rough estimate. Not too bad of an estimate, all right? Pre-calculators, basically, right? So, the error, first of all, we have to talk about vocabulary and notation and things like that. The error we called capital R for remainder, what we called capital E in chapter 11. The remainder or error of a 5th degree Taylor polynomial is called R sub 5, which always indicates the highest power, and then the remainder tells you how far off you are. Normally you put R sub 5 of x. This time we actually put R sub 5 of 2 because we're evaluating at 2, okay? And 2 is kind of close to the center 0, so you'll get decent answers here before this snake departs the sine curve, right? Okay, then how did we find the error? All right, or the remainder in this chapter. Do you remember we took the polynomial p sub 5 of 2, that's the really rough estimate, and we subtracted the real life sine of 2, what we refer to as f of 2, and then we put absolute value bars around it, because error is something that's always positive. And you know what? The bars will make it positive. Maybe because notice this is an alternating series. Positive, negative, right? It's an alternating series for sine and for cosine. Also, we did that one too. Okay, a lot of these are real life alternating series. So because it's an alternating series, the value that it spits out might be too much for the real value, or it might be too little because it's oscillating back and forth. So we need the bars to kind of straighten that out and give us a positive error. And it turned out to be 0.024 when we did it in 12-1. Okay, so that's your first type of error. That's like probably the easiest one. Very, very simple. Now there was a second type of error we did in chapter 11. the alternating series error bound. That's the official way to call it. I don't think that's exactly how we called it before. Maybe, but that's the official title. The alternating series error bound only applies to alternating series. It's an alternating polynomial that could be written as a series. This is from 11-3a. How did we find the error back in chapter 11? This is a good refresher right here. Well, first, we found the infinite sum of the series that we called S sub infinity, and then we subtracted off the partial sum. So let's call it S sub n. We took a partial sum and we said, how far off is that? And then we had to put bars around it because error is always positive. And you actually might get a partial sum that's larger than the final answer of the infinite sum because it went too far and then it steps back. And then it goes too far and then it steps back. Okay? Then we made that less than or equal to what? What was the key in that chapter? Remember that we removed the oscillator and we did the absolute value of the next term, a sub n plus 1. Or the bars will actually remove the oscillator and you could just do b sub n plus 1, which is the part without the oscillator. Or you could do a sub n plus 1, but then you'll see the oscillator will just disappear. Okay, so we did absolute value of b sub n plus 1, and we said that the error is always going to be less than or equal to the next term after that. That will tell you how close you are to the answer. We're going to take this from the last chapter, and what we're going to do is we're going to call this capital R instead of capital E from the last chapter, all right? The remainder, after you do n terms, that could be 49 terms like that one homework problem, that could be 58 terms, 100 terms, whatever. The remainder sub n, where you stopped, of whatever x value you're looking at. Like up here we were looking at 2, okay? That's how you write the remainder. The remainder or error, same thing, must be less than or equal to the absolute value of the next non-zero term. Now, a lot of sources, even on the internet, even reliable sources, fail to mention the non-zero part. They just sort of gloss over that again. This is like a partial gem, I guess, right? A lot of sites get it right, a lot of sites get it wrong, a lot of books get it wrong. Next non-zero term. If the next term is 0, you skip that and go to the next one after that. If you look at your polynomial, this skips x to the 4th and you would jump over to x to the 5th. So if you follow the polynomial, you'll be fine. I'll show you how to do it, okay? But if you're looking at your list, like your 3 columns, and you've got a 0, ignore that, go to the next one. That is very important, okay? All right, so that's chapter 11, chapter 12 refreshers. Let's go over here to the board and apply those things now. Find the maximum error for sine of 2 using the polynomial p sub 5 that we just stated over there. And you might be thinking to yourself, wait a minute, the maximum area, don't we know the real area? Don't we know the actual area? Because wait, don't we know what the sine of 2 is? And didn't we just subtract the estimation at 2 minus the real sine of 2, and then we got an error of 0.024. We already know what the error is. What about before calculators? What about back in the era when they didn't know what the sine of 2 was? But clever mathematicians still found a way to get super close and to know how close they were to the answer without any calculators at all, without really knowing what the sine of 2 is. Isn't that so clever to not know the answer but know how close you are, or at least within what frame, what tolerance? That's amazing to me. That's incredible, all right? Number 19, Gottfried Leibniz. He's the one who came up with this idea right here. Problems like this contain 3 things, yet again. They contain a degree, which is the 5. So that's how far you've taken your polynomial, right? So degree, we'll call it n equals 5, right? We always call the degree n. You'll notice the sub n right over here on the remainder, right? Okay, now what else do you have? You have a center. And remember the center for this problem was a equals 0. We always call the center a, and that was way back in chapter 12 when we did that. And then we also picked what number, so you also have an x. The x is 2, which is kind of close to 0, which means you'll get pretty good estimations, right? Decent estimates. So the x value, all right? So you always have NAX, just remember that, right? Here's what you do. Look back over here. This new way of stating the alternating series error bound, because this is an alternating series, we said that the remainder is less than or equal to the absolute value of the next non-zero term. All right. In your Taylor polynomial, let's write out Taylor poly. Okay? In your Taylor polynomial way over here, I'm going to be like off the screen here practically, but look. What was the next term after where it ended? The next thing after x to the 5th over 5 factorial? Well, x to the 6th over 6 factorial wouldn't exist because you would have a 0. It would become a 0 term. All right? The next non-zero term would go back to minus, according to the pattern, x to the 7th, because it's all the odd powers, over 7 factorial. That's your next term. There is no x to the 6th. If you do the 3 columns, you'll get an x to the 6th with a 0 in front of it. The x to the 6th will drop out. So there's your next term. All right? Now, with the next term, let's plug in the 2 because that's the x value. And the center is built in. It's x minus 0, quantity to the 7th, right? That's the pattern. That's the degree that even led us here in the first place. And now we finish it off. All you have to do is this. R sub 5th degree polynomial, so the remainder sub 5. When 2 is plugged into the Taylor polynomial, the remainder is how far off are you? It would have to be mathematically less than or equal to the absolute value, because error is always positive, remainder is always positive, of what? Negative x to the 7th over 7 factorial. But with the 2 that's here plugged in for x, negative parentheses 2 to the 7th over 7 factorial. Interesting. This is kind of like the b sub n plus 1 we talked about, except this is actually the whole a sub n plus 1. The negative is still in there. But remember, it's really b because the oscillator will get removed. So the negative is going to disappear. The absolute value of that is 2 to the 7th over 7 factorial. So let's say equals, and then you just type that into a calculator. If you type that into a calculator, 2 times itself 7 times in a row over the gigantic number 7 factorial is 0.025. Without even knowing the sign of 2, pre-calculator era, they knew that they were within 0.025 of the actual answer. Can you believe they could do that without knowing the real answer? Stunning. Wait a minute. Didn't we calculate that the actual error, now that we know the sign of 2 on any calculator, every student has a calculator, every phone has a calculator. Didn't we say the error was 0.024? Isn't that less than or equal to 0.025? We said the actual error would be under that number. That's worst case scenario. It's actually a little bit better than that. And there is a third type of error that you learn about in BC calculus and throughout college, called the Lagrange error bound. I wonder who could have discovered that. Of course, none other than number 5 ranked Joseph Louis Lagrange, one of the greatest of all times. You can just spell him Lagrange. All right, Joseph Louis Lagrange, but in French, that's of course pronounced differently. 1797, he publishes this interesting idea that's even better than the error bound we just discussed in 1714 from Leibniz. This one was even better, all right, even more accurate. And he published it in the same book that he published a very famous theorem that you and I discussed in the first semester. The only time we mentioned number 5 Lagrange in the first semester was for the mean value theorem. You remember the MVT, the very last test right before Christmas break? Mean value theorem, all right? Had it in the same book. I mean, man, what a great book that is, right? I'd love to purchase one of the original copies. They sell them for like $3,000. You know, imagine. Okay, so his theorem is his error bound. And I'll ask this on the AP test. They'll say, use the Lagrange error bound. Let me show you how to use it. It's a little abstract, but, you know, I think we can get through it. R sub n of x, the remainder, will be less than or equal to, and instead of over here where we just did the absolute value of the next non-zero term, which you also have to know for the AP test, you're going to do the maximum, whatever the highest amount is, for the absolute value of the n plus first term. So you're going to go to the next term, do the absolute value like over there, but then there's going to be like a range from a to x. What the heck is a to x? Oh, it's the same nax that we listed over here. It's the same thing. You're going to have like a center and then a number that you're estimating, and you're going to, in that window, you're going to find the highest value. Okay, I'll show you exactly how to do it. Now, since we are specifically targeting Taylor polynomials, what they'll target on the AP test, exactly what Lagrange was studying at the time, what is the formula? Remember the magic formula that Euler pioneered, like the modern formula? Remember that it is the nth derivative at the center. You plug in the center over n factorial times x minus center to the nth power. There's your master formula. And Lagrange says, look at this window from the center to wherever you're trying to estimate and go to the next term to try to find the maximum on that interval. What's the next term? That would be the n plus first derivative at the center, right? The next derivative at the center over n plus 1 factorial times x minus center to the n plus 1. So you're simply going to the next term, kind of like we did over here for this Taylor polynomial. Very similar, all right? But even a little bit more advanced and even a little bit better. I mean, that's why he's number 5 all time, because he could pull this out of thin air when nobody else could. I mean, can you imagine in the 1700s? Use a Lagrange error bound to find the maximum error of sine of 2 before calculators compared to plugging 2 into the 5th degree Taylor polynomial. All right, first of all, ingredients. 3 things, 3 ingredients, NaX, NaX. All right, what is N? N is the number of the Taylor polynomial. We went up to the 5th degree, so that is the degree of your Taylor polynomial. They might give you P sub 11. They might give you P sub 3. They can give you whatever. Okay, A, center, 0. We're doing the same problem we did before, right? Where this is the whole highlight of the first page here, sine of x centered at 0. So that's going to be your center. And then finally, there's got to be an x value somewhere that's not the center, because if it was the center, you'd get exact results, right? It is the 2 right there. So 2 is your x value. Okay, get your 3 ingredients. Now, what does this theorem say over here? Okay, Lagrange says that the remainder will be less than or equal to the maximum of the absolute value of what? The n plus first term. Isn't that gigantic, colossal thing we just wrote down here? We're going to take the absolute value of it, and then we're going to find the highest peak on that. That seems really complicated, right? It's okay for you to think this is complex. Okay, it is a little bit. I like to break it down into easy categories. That's what I do as a teacher. I try to make this easy. So let's just break it down into that piece first, the n plus 1 derivative, n plus first derivative. The factorial will do second. The x minus whatever will do third. Notice I put it into 3 categories. Just do one piece at a time. Don't make this crazy. Don't overcomplicate it. All right. Find the maximum of just the absolute value of the n plus first derivative. Just that top piece right there. Okay. Well, what is the function? And then what is its n plus first derivative? Oh, wait. Sine of 2, so the original function is sine of x, right? Let's start with that. F of x equals sine of x. If they put natural log of 2 there, your function would be natural log of x. It's whatever function you're stuffing this into. Okay, now, sine of x, we want the n plus first derivative. N is 5 from that subnumber, so we're going to the n plus first, or the 6th derivative. I need the 6th derivative here, okay, of x, sorry. All right, what is the 6th derivative of sine of x? You don't have to do those whole 3 columns from 12-1. That's a separate problem. You just need to cut to the chase. All right, well, sine's the original function. So first derivative of sine, cosine. Second derivative, negative sine. Third derivative, negative cosine. Fourth derivative goes back to positive sine. Remember the cycle in the first semester? Derivative of sine. The 5th derivative is cosine. The 6th derivative is negative sine of x. So get to the proper derivative. We're going to find the max of the absolute value of the 6th derivative, which is basically the absolute value of negative sine of x, right? On what? On the interval center to where we're estimating. On the interval from center 0 to where we're estimating, which is 2. Pretty much said it, didn't I? Okay, now think of this right here. I want to try to make this a little bit better. Think of this as the absolute value of -1 times the absolute value of sine of x. You can split it up like that because it really is just -1. The absolute value of -1 is 1, right? So that's really just going to be gone. Now sine of x though, sine of x is not always positive. Sine is something that can be above and below the x-axis. You can't just drop the bars right there because this is a thing that can be negative, all right? So you're looking at y equals the absolute value of sine of x. Okay, so we draw a little graph. Hopefully you can still fit this in there right small because I do want you to draw a little graph. What does the absolute value of sine of x look like? Well, here's the first sine hump. It goes from 0 to pi, correct? Where's the next part of the sine? Isn't it a valley to 2 pi? But the absolute value folds everything negative over into positive. So you get this right here to 2 pi. And then you get another one to 3 pi. And it keeps doing that forever, right? Okay, so everything below the x-axis, the absolute value bars fold it and make it positive. Everything above the x-axis was already positive and just stays right where it is. You kind of get the Loch Ness Monster, all right? Okay, so there's the graph. Now block it off from 0 to 2. There's 0. That's 3.14. Pi over 2 is like half of a pi, which half of 3.14 is about 1.57. So you just need to know that 2 lands somewhere in here without a calculator, okay? You don't have to be too fancy, just know that 2's right in here. So what you're saying is, what is the maximum value of this graph from 0 to 2? The highest this ever goes is that peak right above pi over 2, which is 1. And Joseph Louis Lagrange figured out that the maximum value of the graph of the next derivative of the Taylor polynomial actually predicts how accurate your answer is. That's pretty far out if you ask me, all right? So the maximum is, the max is 1. Let's start with that, okay? Now let's go to the much easier part. What is n plus 1 factorial? It's over here in the formula, right? N plus 1 factorial is 5 plus 1 factorial. Remember, we're using the Taylor polynomial to sort of predict the next group, right? So 5 plus 1 is 6. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. You'd be allowed a calculator for this. It's 720. I happen to know that because it's one of the common low factorials when you do them all the time, you just never forget them, all right? Now, what about x minus a to the n plus 1? Okay, isn't x 2? Minus isn't a 0? We're coming to this part of the formula right here, right? So 2 minus 0 to the n plus 1. 5 plus 1 is 6. Okay? 2 to the 6th. Drop the 0. 2, 4, 8, 16, 32, 64, right? That equals 64. Now, why did I pull these out of the bars? Notice over here it says find the maximum of the absolute value of all 3 of these components right here. And notice we did the bars on this column, but I kind of just ignored it over here. I didn't do the absolute value bars. I didn't write the word maximum either. You know why? Because 6 to the factorial is pretty much 6 to the factorial. And 2 to the 6th is pretty much 2 to the 6th. You can't maximize these. They are what they are, right? It is what it is. And then the bars, that wouldn't change because all that stuff's going to be positive anyway, okay? So, now, of course, if this one were negative, you would make it absolute value. But the point is, worry about the maximum of the next derivative. The other 2 will fall into place, and your conclusion, which is off to the side, but I've run out of space, your conclusion, according to this over here, is that the remainder, r sub n, which we're going to call r sub 5, of x, which we're going to call 2, would have to be less than or equal to the maximum of the absolute value, which was 1. That's going to go there. The factorial number was simply 720. And the 64 is what goes right here. No bars necessary because I don't see any negatives now, and we've kind of already dealt with the bars in this column anyway. And if you do 64 divided by 720 on a calculator, you will get the maximum error, the worst case scenario, which just happens to be 0.089. 9. Everything's written to 3 places pretty much in calculus when you do a decimal on your calculator. And I know what some of you are thinking, wait a minute. The actual error was 0.024 from the other day. Leibniz had the idea to do the alternating series bound, which was 0.025, which was pretty close. Lagrange's idea was even worse, and he came up with this like 80 years later. Shouldn't we be better in technology and mathematics and everything else 80 years later? He never claimed that his estimate would be better than Leibniz's idea of the alternating series bound. He said that his remainder or error would work for any series. Do you see where it says alternating series error bound inside that big box towards the top of your notes there? And what does it say? It says that that rule applies to any alternating series. Now, what does the box say for Lagrange error bound? It works for any series. And there are a whole lot of series out there in real life that are not alternating, right? Lagrange's works for all series. And it also has other benefits as well. So it doesn't have to be the best estimate. It's just a breakthrough for any possible series that we don't quite understand yet. All right? So let's apply it on the back page here. Letter C says write a second degree Taylor polynomial for f of x equals e to the x, exponential growth, like classic exponential growth, and x equals -2 will be the center. Just like the cockroaches multiplying back in integrated 3, but boy, have we gone past that now, haven't we, right? Wow. Okay, so remember, n equals 0, n equals 1, n equals 2. All right, you start doing your list, and you have 3 columns. So first column, the 0th derivative, or the original function, e to the x. The second row is the first derivative. N equals 1 means find the first derivative of e to the x. Remember that it's itself. Derivative of e to the x is e to the x. Chain rule is 1. You multiply by natural log of e. That doesn't really matter because it's also 1. And then you do the second derivative, and that's e to the x. See how quickly, now that you get the hang of this, you see how fast you can do this on the AP test, right? You can just rip right through this, okay? And in college, you're going to blow them out of the water, let me tell you. There are going to be other people that are sitting around with you in class in college saying, how are you so well prepared? Because I went to NSA, that's why, because we're the best. Okay, now, second column. A equals -2, the center, which is often 0, not this time. So do f of -2, which is e to the -2nd. Do f prime of -2, which is e to the -2nd. And do f double prime of -2, which is e to the -2nd. It's rarely this, right? But for exponentials, it often is. Last column, which I've conveniently already run out of room. All right, I'll put it down here, you put it up here. Remember your 3 terms, you've got 3 fractions, and remember it's just easier to do all the numerators first. Okay, numerator, 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 isn't it just everything from the second column, these numbers right here, which are the same this time, usually not. E to the -2, all the way down, okay? Boy, those sure are close right there. All right, remember on the bottom, you have 0 factorial, goes there, 1 factorial, 2 factorial. This is the Taylor pattern right here. And then on the side, you have x minus center to the nth power. X minus -2. Minus minus makes a +2 to the 0. X plus 2 to the first. X plus 2 to the second. Okay? Those are your 3 terms. Now you can go back and clean it up a little bit. All right. So this is going to be e to the -2. E is the one thing you can leave to the negative power. You don't have to scoot that to the bottom. It's the one time. That's 1, so drop it. Anything to the 0 power is 1, so drop it. That's your first term. Okay, second term. E to the -2 over 1 factorial is 1, drop it. Keep it. X plus 2. Okay, keep it in parentheses, drop the first power. Third term will be e to the -2 divided by 2 factorial. And remember the very first lesson, 12-1, we went ahead and did the factorial just for fun, but we said you probably don't usually have to, you can just leave it 2 factorial, okay? Or you can do 2 times 1 is 2, whatever. It's up to you. X plus 2 quantity squared. All right, so my Taylor polynomial is going to be capital P sub, what's the highest power? Squared. P sub 2 of x equals simply e to the -2nd plus e to the -2nd times x plus 2. Get out of here. And then plus e to the negative second over 2 factorial, for crying out loud, times x plus 2 quantity squared. All right? And that's all from over there. It's all gone now. There's your second degree polynomial right there to get decent estimates for exponential growth back here at negative 2, left of the origin. Okay? All right. That looks good. Next question. Using a Lagrange error bound, what would be the maximum error of e to the pi? Hey, our two favorite irrational numbers, right? E and pi at the same time. If you took a Taylor polynomial all the way out to the 20th power, which would be pretty accurate, and you plugged in pi, which is a little funny because isn't the center negative 2? So pi's pretty far off, but we're going out to 20 terms. It's kind of a battle of like how many terms you have compared to how far from the center you are. How would you use the Lagrange error bound to figure out how close are we? All right, let me just go through how the other ones fall apart, and you're going to be very glad that I taught you the Lagrange error bound on the front page. Okay, actual error. Not what is it, because it's going to take forever, but just how would you calculate it and why is this bad right now? Actual error is easy, Mr. Wade. Error is always positive. Absolute value of, now what is our, okay, first of all, what's our NAX? If you want to go ahead and list that right now, what is our NAX this time? NAX. Let's go ahead and list that since we're going to talk about it anyway. N is the 20, right? Okay, 20th degree polynomial. A is the center. That's the negative 2 from over there. And x, it's e to the x, but x has been replaced with pi. So when you go to do the actual error, isn't it the absolute value of p sub 20? You plug it into the Taylor polynomial. What's x? That's pi. You can tell it there, right? P sub 20 of pi minus the real f of pi. In other words, the real life e to the pi, right? But here's the problem. Don't you have to have the 20th degree Taylor polynomial just to do this? If you wanted the 20th degree polynomial, okay, look over here. 1, 2, 3 terms, and that was a second degree polynomial. 1, 2, 3, if we had 4 terms, you would have the third degree polynomial. See how the number of terms is always 1 higher than the degree, right? So if you wanted to write out the 20th degree Taylor polynomial, that would take 21 terms. Okay, this is where I want you to see that, you know what? I don't feel like doing 21 terms of that polynomial, even though it's relatively easy, but then wait a minute. What about plugging all that into a calculator and then plugging in the pi for all those x's all the way out for 21 terms? No way, Alternating series error bound, First term positive, second term positive, third term positive, fourth term will be positive. All the terms are positive. It's not an alternating series, okay? Not alt. So guess what? Leibniz's idea doesn't work when it's not alternating, but the Lagrange error bound works for all Taylor polynomials. And it doesn't matter how far you go, 20 or 20,000. His idea works very quickly, all right? Provided you can easily take derivatives. That's one of the keys. Okay, so first of all, what is the f of x, and then what is its n plus first derivative as we start to get used to this together now? What is f of x? E to the pi is actually coming from e to the x. Now, let's do the n plus 1 derivative. If we're going to go out to the 20th polynomial, 20th power, isn't n plus 1 the 21st derivative? But then Lagrange knew that, wait, the 21st derivative of e to the x is still e to the x. So you can predict really deep terms way out there and just use a simple derivative, okay? As long as the derivative is not too complicated, then that could be a problem. Then we have other mathematicians come in to solve that issue. All right, so 21st derivative. Now, what are we looking for? The maximum of the absolute value of that 21st derivative on the window from center to wherever we are right now. The center is negative 2. And then the edge is pi. That's the edge of the interval, or where we're actually plugging in. Kind of far from the center, but not too bad. Not too bad, actually. It could be a lot worse, okay? Let's draw a graph. E to the x, exponential growth. is always above the x-axis. We said that a million times in integrated 3, right? Exponential growth is above the x-axis. It's always positive. The absolute value of a positive is itself. You can actually drop the bars this time. So we are just looking at y equals e to the x without the bars on that interval. Okay, this is the time-consuming part. The other two are really easy, the other two columns. So just figure this out and you're good. All right, close up. Do we know what e to the x looks like? Of course we do. All right, let's graph this. Exponential growth goes right through there. All right, that's 1, but you don't even have to know that right now. You're going to block it from -2, and we'll just call that positive pi right there. Okay, where is this value the highest? Wouldn't it be right there? Isn't it the highest of all the values? And what is that value? If you take pi and you plug it in, you get e to the pi. That's the point pi comma e to the pi. Now, do you always get this thing up here? No, we didn't get it last time. Sometimes you do, sometimes you don't, all right? So e to the pi is the maximum y-coordinate or maximum value of that graph on that interval. Now, let's go over here and do the easy stuff. N plus 1 factorial. N is 20. Lagrange figured out, you just need to do 21 factorial. We'll let a calculator do that, okay? You can't do that in your head. All right, and then x minus a to the n plus 1. X is pi minus the center, -2. Minus -2 makes a +2. Pi plus 2 to the n plus 1. 20 plus 1 is 21. We'll also let a calculator figure that out, okay? So Lagrange figures out that the error, the remainder of the 20th degree polynomial, that was our value up there, that was over here in, of x, which this time is pi. So the remainder of the 20th degree Taylor polynomial at pi must be less than or equal to, that was e to the pi, that goes on the top. On the bottom is the factorial, 21 factorial, I guess I don't need parentheses really after all. And on the side is your pi plus 2 to the 21st. We're simply going to plug that into a calculator, except for back then they didn't have calculators, so they had to estimate all this stuff by hand. Can you imagine? Now, technically, didn't we say there's a set of absolute value bars around the whole thing? So technically, yeah, but didn't we already incorporate the bars right in here? We already applied them to the e to the x. So that's already been applied. Factorials can never be negative, so this really never needs the bars. Really, it's for this graph. Now, this value right here, pi plus 2 to the 21st, okay, there are cases where this could come out to be negative. So the bars are really for that. If you see it's going to be positive, you don't even have to put the bars. If you see this thing's going to be negative, you might want to just fix it and make it absolute value into positive, okay? But the bars will already be applied here. They're not even needed there, so it's really for this last term. Anyway, so it's there, but we're not really seeing a lot of that today. So anyway, you type it into a calculator, and, well, let's say equals. Let's say it's approximately the irrational number 0.00039. Wow. If you go out to 20 terms, you will be within 0.39 of the actual answer. That's pretty awesome. And none of these other rules could do it except for Lagrange's idea. Brilliant. Okay? All right, let's do one more example of an AP type problem. So you have an 8th degree polynomial. It's a Maclaurin polynomial. Interesting. And we're going to plug in 2 and see how far off we are from reality. Okay, and Maclaurin polynomials automatically centered at 0, right? Okay, for f of x, not for e to the x. Okay, we're done with e to the x. That was the end of that. So now we're going on to a new idea where f of x isn't even given. What the heck? We don't even have f of x. Okay, well, just start with the basics. Nax, right? Boy, do we have a nax for doing this, huh? Very corny, cheesy, perfect for Mr. Wade jokes, right? Okay, in 8, it's the sub 8. A, Maclaurin, centered at 0. X, 2, being plugged in. Okay? 802, nax. Now, what do? We find the max of the absolute value of the next derivative, right? F parentheses n plus 1. Okay? Well, now wait a minute. What's the function? F of x. I don't even know. F of x is question mark. They didn't even give me an f of x. Sometimes they won't give you a function. I've seen cases on the AP test where they give you a graph instead of a function. Ah, that's interesting. Now Lagrange says if you're looking for n equals 8, and if that's your estimate polynomial, you should be looking at the n plus first, or the 9th degree polynomial. Guess what? We also don't know that, although we do have a graph, at least, of the 9th derivative conveniently. So let's say graph instead. Okay? So they could do this to you, trying to freak you out, right? All right, what do? What does Lagrange say to do? Find the 9th derivative, and then find the maximum value of the absolute value of the 9th derivative. On what? On a to x. Center, 0, because it's Maclaurin. X, 2, 0 to 2. All right? Look at the picture. From 0 to 2. Just this window right here, this is your 9th derivative graph. We don't even know very many values. It doesn't even matter. Don't worry. We've got the values we need. Now, if you take the absolute value of that graph from 0 to 2, it's all negative except for the zeros. Wouldn't we fold it over? Wouldn't it look like this, basically? And that would be the absolute value of the 9th derivative. And so now it would peak at 5. Instead of valuing at -5, it peaks at +5, right? Okay. What is the maximum value of the absolute value of that graph? Wouldn't it be 5 now? So 5 is your max value of the absolute value of the graph. That's how you correctly do Lagrange error, okay? Then the other two columns are easy, all right? Look at the other two columns, same as before. n plus 1 factorial. 8 plus 1 is 9 factorial, okay? We'll trust a calculator to do that. And then the other category is x minus a to the n plus first. Lagrange says, look over there, that'll help you. And x minus a is 2 minus 0 to the n plus first, which is to the 8 plus 1 is 9. And we get 2 to the 9th. Let a calculator do that, although it's 512. A lot of my calculus students should already know that 2 to the 10th is 1024. So 2 to the 9th is half of that, which is 512. I taught you that in integrated 3, don't you remember? Okay, if you don't worry. Calculator will take care of the rest. So 5, 9 factorial, 2 to the 9th. Lagrange says try all that. And then, in conclusion, the remainder, sub n, or 8, at 2, will be less than or equal to, the 5 goes on the top, that's your max, the absolute value bars have already been applied. The factorial can never be negative, so don't even really need to worry about the bars there. Let's just make sure this last thing isn't negative. 2 to the 9th, that's not negative. So the bars, they're there in spirit, but you don't really need them unless this last term is negative. Then you need to make it positive, okay? So we need to plug all that razzmatazz into a calculator. Put the bars here just in spirit if you want to put that in your notes, but it becomes positive. It's already positive. And when you put that into a calculator, it is roughly 0. What did I write on my notes? Oh yeah, 0.007. Okay, so according to that picture right there, you would be that close to the answer. And so the Lagrange error works even if you don't even have a function, but you have a picture. How about them apples? And finally, that brings us to, I guess, a half gem, as you can see on the paper there. Your half gem of the day is something that some websites don't deal with correctly, and I need you to have the real deal before you go to college and not trust some bogus website. Aren't we supposed to do the maximum of the absolute value of the graph, right? What was the maximum of the absolute value folded version of the graph? Wasn't it 5, right? And that was correct, and that led to the correct answer. Believe it or not, I've seen some websites out there that either their wording is not very clear, or they don't even use the right wording at all. They use no words, or they simply flat out state the wrong thing. They switch this backwards and they say the absolute value of the maximum. That's not the same as the maximum of the absolute value. What would be the absolute value of the maximum up here? Okay, let's go back before we folded it over correctly. Okay? The absolute value of the maximum. The maximum of this U shape, isn't this the highest point and isn't this the highest point before folding it? The maximum value on that interval was 0. That was the highest the graph went. Then if you apply the absolute value of 0, you get 0, not 5. Ooh, that's not even right. And websites will say that out there. So some websites have it right, half of them have it wrong. It's a half gem, all right? So make sure you do the maximum of the absolute value of the graph. Never the absolute value of the maximum value of the graph, because you can see it can give you completely the wrong thing. You might get lucky, you might not, okay? All right, so that's 12-5. Try some of that sample test. We only have one section left, and it's a nice review of kind of everything, all right? And that's pretty much the last new stuff I'm going to teach you this year. But we're going to have fun in 12-6 with a little bit of review, all right? Enjoy.
Hold it now.
It's BC Chapter 5. P sub 11 on the semester. That got the degree. These problems are. Remember this. Isn't that a third derivative is positive cosine. Let's make sense out of all this over here. Doggone it, I got those bars in the freaking stupid. Who wants to go that far, right? Okay, that derivative. You stupid. How would be? Technically, this is inside of an absolute value bar. It's inside of a set of absolute. You stupid. The n plus 1th derivative, right? Or n plus 1st, I guess that would be. There's no such thing as 1th. You dumb idiot.